Welcome to this comprehensive guide to the fascinating world of Neural-Symbolic AI. Here we go over fundamental concepts and mathematical frameworks for implementation. At its heart, Neural-Symbolic AI is an attempt to build a more complete form of artificial intelligence by integrating two different ways of thinking, mirroring Daniel Kahneman's theory of System 1 and System 2 thinking. System 1 would be the neural network. This is your fast, intuitive, automatic thinking. In AI, artificial neural networks are the champions of System 1. They learn patterns from vast amounts of data. A simple neuron's operation can be expressed algorithmically, where inputs are learned weights with a bias and activation function. System 2 is the symbolic reasoner. This is your slow, deliberate, and logical thinking. In AI, Symbolic AI is the master of System 2. It operates on rules and structured knowledge, created with logical rules. Here's an example. Using System 1 thinking, we can quickly match a description with an answer. We are presented with a picture of a dog. What is it? Our fast, intuitive recognition represents System 1. Now, we are presented with an indirect logical statement. At first glance, this doesn't make much sense, but when we break it down and compare the logical meaning, we can answer correctly. In the 1960s, symbolic AI dominated. Early AI research focused on logic and rules. Key developments include the Lisp programming language and Shaky the robot, which navigated using logical planning. In the 1980s, neural networks saw a resurgence with the popularization of the backpropagation algorithm, allowing networks to learn from data. This led to breakthroughs in character recognition. 2010 saw a deep learning explosion. AlexNet's victory in the ImageNet competition marked a turning point. Deep neural networks became state-of-the-art for many tasks, from image recognition to translation. 2020 will mark the neuro-symbolic surge. Recognizing the limits of pure deep learning, major labs, IBM, MIT, Google, began heavily investing in hybrid approaches to combine learning and reasoning for more robust and explainable AI. So why combine the two fields? Because each one solves a problem the other creates. The goal is an AI that learns from the world like a neural network, but reasons about what it has learned like a symbolic system. Let's get into how this is now possible. ROPE is an elegant solution for encoding word position in transformers. Instead of adding a position vector, it rotates the feature vector by an angle dependent on its position. The dot product between a query at position M and a key at position N becomes a score dependent only on the relative position, allowing more robust meaning in every embedding. To apply this to high-dimensional vectors, we group features into pairs and rotate each pair in its own 2D plane, often using complex numbers for an elegant formulation. Here is an example of how this would look in Python. Hyperbolic space has constant negative curvature and its volume grows exponentially, making it perfect for embedding hierarchies like trees. We often visualize it using a Poincare disk, where the boundary is infinitely far from the center. The distance between 2 points U and V is given by the following algorithm, as shown below. For linear computing, we can't use standard vector operations in hyperbolic space. Models like hyperbolic graph convolutional networks, HGCNs, use hyperbolic equivalents for addition and matrix multiplication to respect the space's geometry, creating neat binary structures. Quaternions are a 4D extension of complex numbers. Their non-commutative multiplication makes them ideal for representing 3D rotations. In neural networks, they can holistically represent data like RGB color pixels, capturing relationships between channels. How do these concepts fit together? They are all about creating richer, more structured representations of data. By using symbolic-aware spaces like hyperbolic geometry, we can bridge the gap between continuous neural representations and discrete symbolic logic, enabling a powerful feedback loop for reasoning and explainability. The future of robust, explainable AI likely lies in the integration of neural and symbolic approaches. The choice of mathematical space and representational tools is fundamental to a model's capabilities. While challenges remain, the neuro-symbolic paradigm is one of the most promising pathways toward creating AI that is not only powerful, but also understandable, adaptable, and aligned with human values. Be sure to check out the GitHub for an in-depth look and future implementation.